Welcome everyone to The Explainer. Today, we're diving into something absolutely fascinating. We are going to uncover the invisible mathematical architecture of our reality. You know, so often we just look at the world around us, right? The buildings we live in, the maps we use, our smartphones, and we totally take for granted the invisible rules holding it all together. Math isn't just a bunch of arbitrary rules you memorize in a classroom. It's actually the fundamental software of existence. And today, we're looking way past the textbook definitions to master one of the most iconic, foundational tools in the entire mathematical toolkit. We are decoding the right triangle.
Okay, let's dive into this, because the story behind this math is actually wild. We're talking about Pythagoras, a guy who lived over 2 millennia ago in ancient Greece. And get this, he didn't just run your standard school. He actually led a secret, almost mystical society of mathematicians known as the Pythagoreans. They literally believed that numbers were the foundation of the universe, that they held divine secrets. But the big question we're answering today is this: how exactly does an ancient, fiercely guarded secret from a mystic society, something literally drawn in the sand, end up powering the highly advanced, satellite-based GPS navigation in your smartphone right now? It's a mind-bending journey from ancient philosophy straight into the heart of modern technology.
To really understand how that works, let's establish a rapid micro-level reset of the physical players on the board here. We are dealing with a basic geometric shape built from just 3 lines. You've got 2 shorter lines, which we call the legs, and then that long diagonal connector, the hypotenuse. Actually, the easiest way to picture it is to imagine the legs as a flat floor and a perfectly straight wall. The hypotenuse is just a long ladder leaning up against that wall. It's a really simple, tangible physical reality that we bump into every single day.
Now, what's really interesting about this slide is that tiny square symbol tucked right into the corner where the 2 legs meet. That little box is the universal geometric symbol for a right angle, and it means those 2 lines intersect perfectly at exactly 90 degrees. Not 89 degrees, not 91, exactly 90. This is the absolute rule of the shape we're exploring. The mathematical superpower we're about to discuss only exists and only functions when we have this strict, perfect 90-degree intersection. If that angle bends even a fraction of a degree, the entire rule shatters. It really is the anchor that holds the whole theorem together. So, how do we translate that perfect physical shape into the actual language of math? Well, here is where we bridge the gap. We take the physical shape of the right triangle and translate it directly into the algebraic equation a squared plus b squared equals c squared. Think of it as a direct translation. The a and the b simply represent the measurable physical lengths of our 2 shorter legs, and the c stands for the length of our long diagonal hypotenuse.
We've all heard this equation rattled off in schools, right? A squared plus b squared equals c squared. But the absolutely crucial point here is that these aren't just abstract letters to memorize for a test. This equation is, literally, the grammar of the physical world. It tells us something incredibly profound about distance and space. It dictates that if you take the length of one leg, multiply it by itself, square it, and then add that to the squared length of the other leg, the resulting number will always, flawlessly, equal the square of the hypotenuse. It's like a perfectly balanced scale. If you know the length of any 2 sides of a right triangle, this equation guarantees that you can unlock the exact length of the 3rd side. It is basically a universal lock and key. And this brilliantly illustrates how a seemingly simple rule scales up to solve massive real-world problems. Let's zoom out to the macro level for a second. For centuries, sailors used this exact relationship for ancient sea navigation. By understanding their eastward and northward travel, they could calculate their exact diagonal distance across vast, featureless oceans, making sure they didn't get lost at sea. In construction, builders have used this math for thousands of years, often using knotted ropes actually, to ensure that walls and corners meet at perfect right angles, so buildings stand perfectly straight instead of, well, crumbling down. And today, the modern GPS tracking in your pocket uses these very same geometric principles in 3 dimensions. It calculates the precise distances between your phone and multiple satellites in orbit just to triangulate your exact location on the globe.
It truly brings to life the idea that mathematics is a superpower that allows you to calculate the unknown from the known. You are literally using logic to kind of see distances and relationships that you couldn't possibly physically measure yourself. By mastering the Pythagorean theorem, you make sure you see this equation not just as a hurdle on a math test, but as an incredibly dynamic tool to decode the universe. You are wielding the exact same principles that an ancient secret society discovered, and using them to understand the cutting-edge technology that shapes our modern world today. It's absolute proof that math is beautiful, powerful, and deeply relevant.
If these deep dives expanded your mind, join the mathematical frontier. Please don't miss our next breakdown because we're decoding the universe one notebook at a time. Make sure to subscribe here on the Robo For Education YouTube channel for weekly deep dives. Follow our Substack for the full source documents along with our site, blog, and more. And definitely join our Discord to chat with fellow math explorers. But before you go, think about this. If an ancient equation can perfectly track a satellite thousands of miles in space, what other invisible mathematical laws are currently dictating your life without you even noticing? Keep calculating, and we'll see you next time.